for the data we collected, we used length. So what we did was try to scale the ride up here to this rod right here, which has a known length of 48 inches on the website. So we try to scale it by like using this perspective and then trying to use it or trying to have it in line with this plane right here to get this bar in line. So the height of the bar, obviously 48 inches, and the height of the further bar, which is here, is 48 inches in that plane, but also 36 pixels. So the height of the ride right here in that same plane was 452 pixels, and then we just calculate the ratio between the bar height and the pixel height, and then we just multiply by the pixels to get our length that way. So it's 50.2225 meters.
Feet.
Alright, so with our solution of length, we had to change it to that position versus time graph where you have to calculate x max and angular frequency and everything, right? So this is what we got for our position versus time graph. 8.56 meters was our maximum x difference. And then yeah, our frequency was zero point 0.8 radians per second. And then this bottom graph shows the pendulum x position and the cart position, including the fall time. So the way this works is that the cart speed, 4.8768 meters per second, is being multiplied by the change in time, as well as the change in time, including the fall speed, right? All the work is in this document. I'll show it later. For the time for the fall, it was equal to 2.08 seconds. The location of the ride was originally 14.32 or 33 meters left of the origin being the middle or dead center where the pendulum angle would be 0. And then the second solution of the pendulum would be at 22.02 seconds around, and that's when the pendulum is at 8.09-ish meters to the left of the origin. And then prior to that, before pushing you off, or like the moment before pushing you off, it would be the cart would be at 2.36 meters to the right of the origin. And then going to our next solution, we use period. So basically, I put it into an editing software just to find the timestamps of when it reaches its maximum height, and then reaches its other maximum height, and then once again reaches the next maximum height. So for the blue timestamps, which are these right here, the timestamps were 22.34 seconds, 29.14 seconds, 35.52 seconds, and then for the pink stamps, it's this. And then we just calculate the change in time to get our period, and then I just average them to get the average period. And then once again, we have our pendulum x position versus time, but I also include the y position versus time, where 20 here is going to be like just the height of the pendulum above wherever. We just assume 20 meters. And then for the pendulum x position, it's the same scheme as last time, where it was the x position and then plus the cart position, including the fall time. So basically, that helps us with wherever it intersects. That's just going to be the time, which is the x coordinate, and the location of the cart where when you push yourself off, or when the TikTokers push you off. So for the time for the fall, it was 2.1-ish seconds, and the location of the ride prior to pushing you off or like the moment before pushing it off was 15.29 meters left of the origin, and then our second solution was 10.81 meters to the right of the origin. So we also had our data with angular velocity. We were going to use this by integrating it and then finding position that way, because that's the formula. And then yeah. So I'm going to show you this document real quick. So it shows us how we gathered the height, right? Pixel of the bar, height of the bar, ratio of the bar into the picture what we use, the period, once again, the timestamps and everything, and then time intervals and everything. So this is how I calculate the maximum angle. So I basically had to like make this triangle and then use a protractor and scale it in a way that it could accurately measure the maximum angle at its peak. I also try to like find like or like I Photoshop it at its max peak on the left side and also on the right side and also when it's like dead center. And then I try to use this triangle to find the degree angle, which was 34 degrees. So for like solving the math and everything, it was just, oh, I measured the length. Now I'm finding period, then angular frequency. Then I'm using finding x max, and then whatever x max is, I use in the equation, and that gives me the position versus time graph. And then I get the y position versus time graph, and then also the graph of the cart without any change in the or including the false peak. So yeah, this is also the graph of like the fall time and like depending on the certain time, there's gonna be a y height, and then it's gonna have a certain false fall acceleration depending on that or fall time. And then there's just more to this, more math and everything. It just shows my foolproof. Right, the best solution is finding the period. It's because it can be very precise when measuring and no assumptions really need to be made. And the multiple trials can be done very easily. It can be precise to maybe like the 10,000th place of a second, depending on like what software you're using and how good your recording software is. So with that, it's very precise. There's like little room for error. And then there isn't really any assumptions being made because you're only like differentiating between a frame or two, which is basically 10 milliseconds or a millisecond at most. And the multiple trials can be done very easily with this method because all you have to do is record the video and then just watch it swing back and forth, and those are in multiple trials. And also you can record multiple videos which each have multiple trials, so gaining data is very easy. There's no assumptions really being made, and it's very precise. Compared to finding the length the way I did it, it was really inaccurate and not precise at all because you had to do a lot of assumptions, a lot of assumptions with the way the camera is warping, the assumptions of if like that scaling of the bar was correctly put in the same plane as the pendulum. There was just so many assumptions there. And then also with um, the angular velocity that we were gathering, that could also be have room for error because our phone can be like jostling within our pockets, and that changes and messes up the data a lot, and that could have a serious impact on our data as that jostling could last for like a second, and that would be like 1,000 data points um, that are infected with terrible data, not good or quality data.